Large Hadron Collider is the world's biggest atom smasher.
Found the God particle. That was our main thing. Done. I've got some ideas for smaller things to do, but we did the big one.
There is a tunnel, and machinery inside that tunnel sends beams of energy in a vast circle.
Scientists just opened a doorway to another dimension, which could be the last huge mistake by CERN. Just 10 days later, photographer Christophe Suarez shared photos of the skies above the organization. The photos were stunning and showed strange clouds forming. Could this be evidence that the world's biggest experiment is about to destroy everything? Let's find out what nightmares the other dimension holds for us. Higgs boson, unanswered questions. Until recently, the idea of opening a portal to another world was something you'd only expect to see in movies. This concept has become a real concern, stirring a mix of anxiety and curiosity among people. Questions are circulating. What will happen to us? Is our world at risk of being destroyed, or will we encounter our doubles in another dimension? Amid these fears, the re-emergence of the European Organization for Nuclear Research has brought even more uncertainty. Today, we're diving into the possibility that there might be a gateway to a parallel universe. The European Organization for Nuclear Research typically enters the public eye when there's news of a subatomic particle being found. It operates the world's largest particle physics lab, which includes the massive Large Hadron Collider. This collider is a huge ring, almost 17 miles in circumference, located underground. It's known for being the most powerful particle accelerator in the world, meaning it can push subatomic particles to speeds incredibly close to the speed of light. The Large Hadron Collider's main job is to test the theories of particle physics by smashing atoms together at these high speeds. This process recreates conditions similar to those just after the universe began. This intense experimentation helps scientists look back at the very start of the universe, offering clues about how everything started. The collider made headlines worldwide in 2012 when it discovered the Higgs boson, which many people call the God particle. This particle is very special because scientists think it can help explain how the universe got started and support the Big Bang theory. This theory suggests that an invisible force filled the entire universe right after it began, giving mass to everything. Finding the Higgs boson helps confirm the standard model of particle physics, which is a set of rules believed to govern the basic particles of matter. The work being done at the European Organization for Nuclear Research might lead to groundbreaking discoveries about our universe, but it also brings a lot of worry. If researchers at the European Organization for Nuclear Research have truly found a way to open doors to other dimensions, what are the implications for us all? Could this scientific breakthrough bring unknown risks into our world? The possibility of entering unknown spaces is exciting for some, but deeply frightening for others. As we probe deeper into these scientific frontiers, the line between what's real and what's possible in science becomes increasingly unclear, challenging our understanding of what we know about the universe and raising profound questions about what might lie beyond our current realm of knowledge. This exploration into other dimensions could redefine our perception of reality, suggesting that our universe might just be one of many. The implications of such a discovery would be profound, affecting not only the fields of physics and cosmology, but also our philosophical understanding of existence. The idea of multiple universes, each with its own laws of physics, and perhaps even versions of ourselves, pushes the boundaries of imagination and scientific inquiry. As we stand on this precipice, looking into the vast unknown, the work at the European Organization for Nuclear Research continues, possibly bringing us closer to answers that could forever alter our grasp of the cosmos. Now that scientists have found the Higgs boson, they are focusing on an even more challenging goal at the Large Hadron Collider. This goal involves exploring dark matter and dark energy, which are invisible forces that hold galaxies together and make up over 95% of the universe. Although these elements are all around us, they have never been directly seen. We only know about them because of the gravitational pull they exert on visible matter. Jen Liu, an astrophysicist at the University of Minnesota, mentioned in an an email to the Daily Galaxy that the Higgs boson, an important part of the standard model in physics, might also serve as a gateway to connecting with the unseen parts of the universe, such as dark matter and dark energy. Some scientists think that there is a specific type of dark particle that hardly ever interacts with the matter we can see and touch. There's hope at the Large Hadron Collider that these rare dark particles might show up during the proton collisions that happen there regularly. Liu is hopeful about the prospects of directly observing these elusive particles. He suggests that using quantum mechanics might allow scientists to detect the changing states or decay of these dark universe particles. Moreover, with the advanced techniques developed for managing Higgs boson experiments at the collider, there's a chance that scientists might soon be able to produce and recognize particles from this dark sector. Building on this, a group of physicists recently proposed that dark matter could be linked to a particle that has the ability to move to a fifth dimension. Their research, published in the European physical journal C, introduced equations that suggest the existence of an extra dimension could have significant implications for our understanding of the universe and might change what we think we know about reality. This approach to dark matter introduces the idea that our universe is much more complex than previously thought, potentially featuring additional dimensions that play a crucial role in the fundamental physics of our world. This ongoing research not only deepens our knowledge of the cosmos, but also opens up the possibility of discovering entirely unknown dimensions of reality. The concept of hidden dimensions affecting everything from gravity to the structure of space itself could revolutionize our scientific foundations. Next, scientists are digging even deeper into the fascinating puzzles of dark matter and hidden dimensions that could change everything we know, discovering the invisible universe. As researchers delve deeper into these theories, they might uncover new scientific methods and technologies, or they could find challenges that we are currently not equipped to manage. The exploration of these hidden elements is thrilling, but also brings with it a level of uncertainty about the implications for our understanding of the universe. This scientific travel, while exciting, is filled with unknowns that could either expand our capabilities or pose new questions about our existence and the universe we inhabit. Scientists are studying particles called fermions, which might travel through gateways into a new dimension they call the fifth dimension. Here, these fermions could become what's known as fermionic dark matter. This theory suggests a link between the ordinary matter we see around us and the dark matter, which might be made up of these special fermions in another dimension. Liu, one of the researchers, expressed awe at the potential future where humans might control both visible and dark matter. He pointed out the need for more power than even the Large Hadron Collider, the giant machine that found the Higgs boson, could provide. Scientists have already spent £21 billion trying to reach the energy levels required. The Large Hadron Collider was shut down in December 2018 for extensive upgrades. After 2 years of improvements, it started again in April, stronger than before. This new phase, called its third run, aims to explore deeper into the laws of physics. It is now equipped to be the most powerful version of itself, raising hopes for new discoveries. A project support manager shared his excitement about the third run, highlighting the enhanced quality of data from the more powerful collisions and the improved condition of the detector. Everything is now ready for the potential discovery of the particle. Liantao Wang, a professor at both the Enrico Fermi Institute and the Kavli Institute for Cosmological Physics at the University of Chicago, emphasized the importance of asking the right questions to possibly uncover this particle. But alongside these scientific advances, there has been a wave of concern. When the Large Hadron Collider began operating again on April 22nd, rumors started circulating that the European Organization for Nuclear Research was trying to open a gateway to a frightening place while searching for the so-called God particle. This wasn't a new type of concern. In 2016, strange clouds and electrical activity above the European Organization for Nuclear Research facility led to media frenzy. At that time, the Large Hadron Collider was also associated with discoveries of tiny black holes, which some think might show that there are other dimensions. These events have led people to worry more, especially now that the European Organization for Nuclear Research is more powerful, Elon. The fear is that what were once just odd occurrences could now lead to more intense and alarming situations. Stephen Hawking, a famous physicist, once gave a serious warning about the potential dangers of the God particle. Even though he bet Gordon Kane $100 that scientists would not find the Higgs boson, he expressed deep concerns after its discovery. In his well-known book, Starmus, he suggested that this particle could potentially lead to the end of the universe. He explained that if energies reached above 100 billion giga-electron volts, the stability of the Higgs potential could dangerously deteriorate. The Higgs boson, also known as the Higgs particle, is an essential element in particle physics. It was first proposed in 1964 by Peter Higgs, along with theorists Francois Englert, Robert Brout, Gerald Guralnik, Carl Richard Hagen, and Thomas Walter Bannerman Kibble. This particle is a key part of the Standard Model, which explains the smallest parts of matter and how they interact. This particle relates closely to the Higgs field, a field that exists everywhere in space. This field is responsible for giving mass to fundamental particles, such as electrons and quarks, which are the basic building blocks of all matter. If this field were not there, these particles would have no mass and would move through space as fast as light, similar to light particles known as photons. Discovering the Higgs boson in 2012 was a groundbreaking event in the field of physics. It was found during experiments at the largest and most powerful particle accelerator in the world. This machine speeds up protons to almost the speed of light and then crashes them into each other. From these high-energy crashes, a variety of particles emerge, including the Higgs boson for a very short time before it changes into other particles. This brief appearance was recorded by advanced detection devices that are able to catch the particles that come from the decay of the Higgs boson and check them against what scientists had predicted. Confirming the Higgs boson's existence supported the accuracy of the Standard Model and provided more understanding about our universe. The Higgs boson is very unstable and breaks down almost as soon as it forms. By studying how it decays, physicists can learn more about the properties of the Higgs boson and other important particles. The role of the Higgs boson is very important because it helps explain why particles have mass, which is a fundamental aspect of our understanding of the universe. Before their interactions with the Higgs field, particles had no mass. However, after the universe cooled down from the Big Bang, particles began to interact with the Higgs field and gained mass. Searching for the Higgs boson pushed the boundaries of what technology and science could do, leading to significant improvements in the technologies used for particle accelerators and detectors. The research did not stop with its discovery. Ongoing experiments are focused on learning more about the Higgs boson's characteristics and investigating whether there are other types of Higgs bosons, as some advanced theories suggest. With new discoveries on the horizon, we will explore how the Higgs boson has profoundly transformed our understanding of the universe and its origins. The search for mass origins. Although sometimes called the God particle because of its fundamental role in giving mass to other particles, this nickname is not favored by many scientists, including Peter Higgs himself. This name became popular through a book by physicist Leon Lederman. The significant finding of the Higgs boson was honored with the Nobel Prize in Physics in 2013, awarded to Peter Higgs and Francois Englert. They were recognized for their theoretical predictions, which anticipated the existence of this particle. Understanding the Higgs boson and the field associated with it is crucial for the fields of particle physics and cosmology. It helps scientists learn about the early stages of the universe, explaining how particles came to have mass and how the universe developed after the Big Bang. The ongoing research into the Higgs boson and its interactions is a major focus in modern physics, potentially influencing our understanding of the fundamental forces and particles that compose the universe. This research could open up new possibilities in our understanding of the universe. offering insights into the very foundations of matter and the forces that operate within it. Hawking's worry centered on the possibility that small black holes might form and grow, eventually causing internal destruction of the universe. Although scientists at the European Organization for Nuclear Research have reassured the public that these black holes are not a threat to our universe, British astronomer Sir Martin Rees supported Hawking's view. He warned that these black holes might release an unstable form of high-energy, strange matter, which could lead to a disastrous event where time and space collapse. Hawking highlighted that such a catastrophic event could occur suddenly and without any prior signs. While he believed that the likelihood of this happening soon was low, he emphasized that the potential instability of the Higgs at high energies should not be ignored. Researchers are fascinated by the potential influence these particles might have on the universe, possibly creating powerful gravitational waves that could be detected by future technologies. The hunt for the God particle continues, and for now, its discovery remains uncertain. The Large Hadron Collider is set to operate for another 2 years. After the end of its third run in 2024, it will be shut down for further upgrades. These improvements aim to enhance its capabilities significantly, preparing it for its relaunch in 2028 as the High Luminosity Large Hadron Collider. The development of new particle accelerators is also on the horizon. The International Linear Collider in Japan and the Compact Linear Collider at the European Organization for Nuclear Research are two upcoming linear accelerators dedicated to studying the Higgs particle more closely. Furthermore, the Future Circular Collider at the European Organization for Nuclear Research and the Circular Electron-Positron Collider in China are examples of circular models being developed. The Particle Collider in China is projected to be 5 times as powerful as the current Large Hadron Collider, promising even deeper insights into the nature of particles. As the race to uncover the questions of the God particle accelerates, Europe and China are at the forefront. This ongoing quest not only aims to discover more about the fundamental particles of our universe, but also holds the potential to reveal whether this discovery will be a breakthrough for humanity or a trigger for catastrophic consequences. The world watches anxiously, wondering whether the outcomes will introduce us to the creator of the universe or its potential destroyer. Let's take a closer look at the European Organization for Nuclear Research. This institution, which came into being in 1954, stands as a pivotal center for scientific research on a global scale. Located near Geneva, spanning the border between France and Switzerland, the European Organization for Nuclear Research was established to ensure that Europe remained at the forefront of advances in physics, preventing the migration of its top scientists to America in the aftermath of World War II. The aim was also to foster a sense of unity and collaboration among European nations still recovering from the ravages of war. The concept of the European Organization for Nuclear Research was first introduced in the 1940s by a visionary group of scientists who recognized the need for a collaborative research environment in Europe. Key figures in this initiative were Raoul Dautry, Pierre Auger, and Lou Kowarski from France, Eduardo Amaldi from Italy, and the renowned Danish physicist Niels Bohr. The push to establish a dedicated atomic physics laboratory in Europe gained momentum when French physicist Louis de Broglie proposed the idea in 1949. This proposal received a significant boost at the UNESCO General Conference in Florence in 1950. Where American Nobel laureate Isidore Rabi advocated for the creation of regional scientific facilities to promote international cooperation. In December 1951, a critical meeting in Paris marked a significant step towards the realization of this vision, with the adoption of a resolution to establish what would eventually be known as the European Organization for Nuclear Research. By February 1952, an agreement was signed by 11 countries to form a provisional council, leading to the birth of the name CERN, derived from its French title, Conseil Européen pour la Recherche Nucléaire. The decision to locate the laboratory in Geneva was confirmed by a local referendum in 1953. The formal agreement, the European Organization for Nuclear Research Convention, was signed in July 1953 and gradually endorsed by 12 founding member states, including Belgium, Denmark, France, Germany, Greece, Italy, the Netherlands, Norway, Sweden, Switzerland, the United Kingdom, and Yugoslavia. Official operations at the European Organization for Nuclear Research began on September 29, 1954, after the necessary ratifications by France and Germany. Looking back, we delve into the origins of the European Organization for Nuclear Research and its crucial role in advancing global scientific knowledge. Building the last particle lab. The European Organization for Nuclear Research's creation was driven by a dual purpose: to prevent the loss of Europe's scientific minds to the United States, and to rebuild a sense of community among European countries through shared scientific pursuits. This was a strategic move to regain scientific independence and re-establish Europe as a leading force in the scientific world. The establishment of the European Organization for Nuclear Research also represented a significant step towards rebuilding Europe's intellectual infrastructure, offering a platform for scientists from various countries to collaborate on groundbreaking research in nuclear physics. The founding of the European Organization for Nuclear Research was more than just the creation of a research facility. It was a crucial step in healing the wounds of a continent torn apart by war. By bringing together the brightest minds from across Europe, the European Organization for Nuclear Research served as a symbol of hope and unity, using science as a bridge to overcome historical divisions. It was about laying the groundwork for a future where knowledge and cooperation could prevent the conflicts of the past. This vision of unity through science was a bold response to the challenges of the time, reflecting a deep commitment to using research as a tool for peace and development. Through its research and discoveries, the European Organization for Nuclear Research has not only contributed significantly to our understanding of the physical world, but has also played a pivotal role in fostering international cooperation in science. Its achievements in particle physics have had profound implications, influencing various fields of study and contributing to technological advancements. The collaborative environment at the European Organization for Nuclear Research continues to draw scientists from around the world, making it a central figure in the quest for knowledge and a testament to the power of international collaboration in advancing human understanding. The European Organization for Nuclear Research focuses purely on scientific research. It aims to understand fundamental science and ensures everyone can access its discoveries. The European Organization for Nuclear Research does not work on any military projects. It started with building big machines called accelerators that speed up particles for experiments. The first one, called the synchrocyclotron, was built in 1957, followed by another called the proton synchrotron in 1959. These early projects helped the European Organization for Nuclear Research make several important scientific findings. In the 1970s, the European Organization for Nuclear Research scientists discovered something called neutral currents in 1973, and they started using a bigger accelerator, the super proton synchrotron, in 1976. These were key moments for the organization. The 1980s brought more success when the European Organization for Nuclear Research scientists discovered particles known as W and Z. This discovery was so significant that Carlo Rubbia and Simon van der Meer won the Nobel Prize in Physics in 1984 for their work. One of the European Organization for Nuclear Research's biggest contributions to the world was the invention of the World Wide Web. In 1989, a British scientist at the European Organization for Nuclear Research named Tim Berners-Lee proposed a new way to manage information. His idea led to the creation of the Internet, changing how we communicate and share information across the globe. Today, the European Organization for Nuclear Research is not just about building and running these big machines. It's a place where scientists from all over the world come to work together. They conduct experiments and create new technologies that help in many areas, not just physics. For example, the technology developed at the European Organization for Nuclear Research has helped improve computers, medical imaging machines, and even treatments for cancer. The European Organization for Nuclear Research is more than a laboratory. It's a symbol of how countries can work together peacefully through science. It shows how sharing knowledge and working together can lead to great discoveries that benefit everyone. The European Organization for Nuclear Research's open approach to science helps spread knowledge around the world and inspires new generations of scientists. This way of working and sharing is why the European Organization for Nuclear Research continues to be a leader in scientific research, helping us understand more about the universe and improving our everyday technologies. The European Organization for Nuclear Research is renowned for its significant role in advancing our knowledge of the universe through high-level scientific research and collaboration across countries. Starting as an ambitious project, the European Organization for Nuclear Research has grown into a leading research hub, focusing on understanding the fundamental elements that make up our world and the forces that drive the universe. Central to the European Organization for Nuclear Research's achievements is the Large Hadron Collider, the biggest and most powerful particle accelerator ever built. Situated near Geneva, Switzerland, this gigantic structure consists of a ring of superconducting magnets stretching 16.7 miles. It was constructed over a decade, from 1998 to 2008. Involving more than 10,000 scientists and numerous universities and labs from across the globe. The idea for the Large Hadron Collider was first discussed in the 1980s. Its purpose was clear: to explore and answer basic questions about the particles and forces that constitute our universe. The accelerator was strategically built in a tunnel that had been previously used by another collider, optimizing the use of existing facilities. Approval for the Large Hadron Collider came in 1994 from the European Organization for Nuclear Research Council, with a detailed plan following in 1995. Contributions from countries like Japan, the United States, and India were crucial in pushing the project toward completion. Now, we examine the major achievements of the Large Hadron Collider and its ongoing quest to uncover groundbreaking answers about our universe. The collider's horrific impact. The Large Hadron Collider's main function is to speed up two beams of high-energy particles in opposite directions and then make them crash into each other. These particles travel at speeds almost as fast as light, contained in separate vacuum tubes to avoid air resistance. They are directed around the accelerator ring by incredibly strong magnetic fields, produced by superconducting magnets. These magnets operate at extremely low temperatures of -271.3 degrees Celsius, made possible by cooling them with liquid helium. This cold temperature is necessary to turn the magnets superconducting, a state where they can carry electric currents without losing energy to resistance. This huge and complex machine allows scientists to simulate and observe conditions similar to those just after the Big Bang, the massive explosion thought to have created the universe. By examining the particles produced in these high-speed collisions, Researchers can gather clues about both the building blocks of matter and the origins of mass, which are crucial for understanding the universe's structure and history. The experiments conducted at the Large Hadron Collider could potentially lead to revolutionary discoveries about how everything in the universe is put together, from tiny atoms to vast galaxies. The ability to generate such extreme conditions and observe the resulting particle interactions is both awe-inspiring and somewhat daunting. The data gathered from these experiments could change our understanding of the physical world, offering new theories and possibly new technologies. While the Large Hadron Collider represents a pinnacle of human achievement in science, it also highlights the power of global cooperation. Scientists from around the world come together at the European Organization for Nuclear Research, sharing knowledge and resources in pursuit of common goals. This collaboration is a testament to the importance of working together to solve complex problems that no single country could tackle alone. On September 10, 2008, the Large Hadron Collider at the European Organization for Nuclear Research was turned on for the first time. This event marked the beginning of what is considered the biggest scientific experiment in history. The Large Hadron Collider can create up to 600 million particle collisions every second, mimicking the conditions that existed just moments after the universe was born. While this scale of experimentation is groundbreaking, it initially raised significant concerns among some scientists and environmental advocates. They were worried about the potential for creating mini black holes, which could theoretically pose unknown risks. However, these fears were thoroughly investigated and ultimately debunked by experts at the European Organization for Nuclear Research and prominent physicists like Stephen Hawking, who confirmed the safety of these experiments. The goals of the Large Hadron Collider extend far beyond the initial discovery of the Higgs boson, a particle that plays a crucial role in giving mass to other particles. The Large Hadron Collider aims to examine this particle in much more detail to better understand its properties. It also seeks to discover new particles that have been theorized but not yet detected, such as those predicted by theories like supersymmetry. Additionally, the Large Hadron Collider is used to explore the strange components of the universe known as dark matter and dark energy, which together make up most of the universe's mass and energy, but remain largely invisible and undetectable with current technology. Another key area of research at the Large Hadron Collider is the imbalance between matter and antimatter. Scientists are puzzled by why the observable universe is predominantly made of matter when theories predict equal amounts of matter and antimatter should have been created during the Big Bang. The Large Hadron Collider also studies quark-gluon plasma, a state of matter that is thought to have existed right after the Big Bang, which might offer clues about the universe's early moments. The Large Hadron Collider features 4 main areas where these high-energy particle collisions are observed and analyzed, each equipped with specialized detectors designed for specific types of research. These detectors are known as a toroidal LHC apparatus, compact muon solenoid, LHC Beauty, and a large ion collider experiment. Each of these experiments is tailored to investigate different aspects of the particles and phenomena that arise during the collisions. To prepare the particles for collisions in the Large Hadron Collider, a complex series of machines gradually increase the energy of particle beams. This sequence starts with simpler linear accelerators and moves through several stages, including the proton synchrotron and the superproton synchrotron, before the particles are finally injected into the Large Hadron Collider. This step-by-step increase in energy ensures that the particles reach the extremely high energies needed for the Large Hadron Collider experiments. Since its first launch, the Large Hadron Collider has undergone several upgrades to improve its performance and expand its capabilities. These include shutdowns from 2013 to 2015 and another from the end of 2018 to April 2022 for maintenance and further enhancements. Such upgrades are crucial for enhancing the collider's ability to conduct high-level experiments and for enabling more advanced scientific research. The upgrades have allowed scientists to explore new physics beyond the standard model, leading to discoveries such as the Higgs boson. The increased luminosity and collision energy have also facilitated more precise measurements of known particles. These advancements ensure that the Large Hadron Collider remains at the forefront of particle physics research. The impact of the Large Hadron Collider on the field of particle physics has been substantial, offering deeper insights into the basic structure of matter and the forces that hold the universe together. Its discoveries continue to influence our understanding of the physical world and drive forward the development of new theories and technologies. As the Large Hadron Collider continues to operate and receive upgrades, it remains a key player in the world of scientific exploration, constantly pushing the boundaries of human knowledge. This relentless pursuit not only deepens our understanding of the universe, but also occasionally brings us face to face with the powerful and sometimes daunting aspects of nature, highlighting our ongoing quest for knowledge and the responsibilities that come with it. Are these strange cloud formations above the European Organization for Nuclear Research just a natural phenomenon? Or could they be a sign that we are on the verge of opening a portal to another universe? We want to hear your thoughts. Tell us what you think. And don't forget to like and subscribe for more.